Holding relays' primary purpose extends beyond mere worker convenience and significantly contributes to safety in many industrial applications. While convenience can be a secondary benefit, the core function of a holding relay is to maintain a circuit state even when the initial triggering signal is removed. This is vital for preventing unintended machine operation or hazardous conditions that could arise from a momentary power loss or signal interruption. Imagine a large industrial press. If the operator had to continuously hold a button to keep the press running, fatigue could lead to errors, and the press could stop mid-cycle, creating a dangerous situation. A holding relay latches the on state, allowing the operator to release the button while the press completes its cycle safely. If a power failure occurs, the holding relay de-energizes, stopping the press and preventing it from restarting unexpectedly when power is restored. This fail-safe mechanism is crucial for protecting workers and equipment. Many types of equipment rely on holding relays to ensure safe and reliable operation. Consider automated assembly lines, robotic systems, and complex machinery. Without holding relays, these systems would be far more susceptible to malfunctions and hazards. The consequences of such failures could be severe, ranging from product damage to serious injuries. Therefore, the primary reason for using holding relays is undoubtedly safety, ensuring that equipment operates as intended and that potential risks are mitigated. Holding relays are also utilized in emergency stop circuits. When an emergency stop button is pressed, the holding relay immediately cuts power to the machinery, bringing it to a halt quickly and safely. This is a critical safety feature in environments where hazards can arise suddenly. The holding relay remains energized until the emergency stop button is reset, preventing accidental restarts. Another key aspect is the role of holding relays in preventing oscillations or chattering in control systems. Without a holding relay, a momentary signal might cause a device to rapidly switch on and off, leading to wear and tear, instability, and potential damage. The holding relay smooths out these fluctuations, ensuring stable and reliable operation. Considering the materials that exhibit the best electrical conductivity, the common sequence of gold, silver, copper, and aluminum is not entirely correct. The order of conductivity from best to worst is silver, copper, gold, aluminum, magnesium, zinc, cadmium, nickel, iron, platinum, lead, solid mercury, and steel. Silver possesses the highest electrical conductivity among common metals. This means that silver allows electrons to flow through it with the least resistance. Copper is a close second, offering excellent conductivity at a lower cost than silver, which makes it a widely used material in electrical wiring. Gold comes in third in terms of conductivity. Gold is highly resistant to corrosion, making it suitable for applications where reliability is critical, such as in electronic connectors. Aluminum is also a good conductor, but it is less conductive than silver, copper, and gold. Aluminum is lightweight and relatively inexpensive, which makes it a popular choice for overhead power lines and other applications where weight is a factor. Magnesium, zinc, cadmium, nickel, iron, platinum, lead, mercury, and steel are all less conductive than the other metals listed above. These metals are typically used in applications where conductivity is not the primary concern or where other properties such as strength, corrosion resistance, or cost are more important. The conductivity of a material is determined by the number of free electrons available to carry charge and the ease with which these electrons can move through the material. Metals with high conductivity have a large number of free electrons and a crystal structure that allows these electrons to move easily. Resistance is the opposition to the flow of electric current in a material. The higher the resistance, the lower the conductivity. Resistance is measured in ohms. The resistance of a wire depends on its material, length, and cross-sectional area. Longer wires have higher resistance, and thicker wires have lower resistance. The resistivity of a material is a measure of its resistance per unit length and cross-sectional area. Materials with low resistivity are good conductors, while materials with high resistivity are poor conductors. Conductivity is the reciprocal of resistivity. The conductivity of a material is affected by temperature. In most metals, conductivity decreases with increasing temperature. This is because high temperatures cause the atoms in the metal to vibrate more, which interferes with the flow of electrons. In some semiconductors, conductivity increases with increasing temperature. This is because higher temperatures cause more electrons to be released from the atoms, increasing the number of free electrons available to carry charge. Factors such as impurities and imperfections in the crystal structure can also affect the conductivity of a material. Impurities can scatter electrons, reducing their mobility and lowering conductivity. The electrical conductivity of different metals varies significantly, impacting their suitability for various applications. For instance, silver is the best conductor, but its high cost limits its use to specialized applications. Copper's excellent conductivity and affordability make it the standard for electrical wiring in buildings and appliances. Coal's corrosion resistance makes it ideal for electronic connectors, where reliable connections are crucial. Aluminum is used in overhead power lines due to its lightweight and reasonable conductivity. Understanding the properties of different conductors is essential in electrical engineering and design. It allows engineers to select the appropriate materials for specific applications, ensuring optimal performance, safety, and cost-effectiveness. Considering the National Electrical Code, NEC, it provides guidelines and standards for safe electrical installations. These standards cover various aspects of electrical systems, including conductor sizing, insulation, and grounding. Adhering to the NEC is essential to prevent electrical hazards and ensure the safety of people and property. The NEC tables, such as Table 310.15b16, provide ampacity ratings for different types of conductors based on their size, insulation, and installation conditions. Ampacity is the maximum current that a conductor can carry continuously without exceeding its temperature rating. These tables help electricians and engineers select the appropriate conductor size for a given application, ensuring that the conductors do not overheat and cause a fire. The NEC also specifies requirements for grounding and bonding to provide a low impedance path for fault currents to return to the source. This helps to protect people from electric shock and prevent damage to equipment. Grounding and bonding are critical safety measures in electrical systems. The NEC covers a wide range of electrical systems, including residential, commercial, and industrial installations. It is updated every 3 years to reflect changes in technology and best practices. Electricians and engineers must stay up to date with the latest NEC requirements to ensure that their installations are safe and compliant. The NEC also addresses the use of different types of equipment, such as circuit breakers, fuses, and surge protectors. These devices are designed to protect electrical circuits from overcurrents and overvoltages. Circuit breakers and fuses interrupt the flow of current when it exceeds a certain level, preventing damage to equipment and reducing the risk of fire. Surge protectors protect sensitive electronic equipment from voltage spikes caused by lightning or other disturbances. Selecting the appropriate protective devices is crucial for ensuring the reliability and safety of electrical systems. The NEC also provides guidelines for wiring methods, such as the use of conduit, cable trays, and direct burial cables. These guidelines ensure that electrical wiring is properly protected from physical damage and environmental factors. Proper wiring methods are essential for maintaining the integrity and reliability of electrical systems. The NEC also addresses the installation of specific types of equipment, such as transformers, generators, and motors. These guidelines ensure that these devices are installed safely and in accordance with manufacturers' recommendations. Proper installation of equipment is critical for ensuring its safe and reliable operation. The NEC also covers the inspection and testing of electrical systems. Regular inspections and testing can help to identify potential problems before they lead to failures or hazards. Qualified electricians and inspectors can perform these inspections and tests to ensure that electrical systems are safe and compliant. The NEC is a comprehensive set of standards that provides guidance for the safe and reliable installation and operation of electrical systems. Adhering to the NEC is essential for protecting people and property from electrical hazards. Considering conductor properties, the conductivity of a material is influenced by its atomic structure and the mobility of electrons within that structure. Silver's high conductivity stems from its electron configuration, which allows for a high density of free electrons that can easily move through the material. Copper, while slightly less conductive than silver, is still an excellent conductor due to its similar electron configuration. Gold's conductivity is lower than copper's due to differences in its electron structure and the presence of more electron scattering centers. Aluminum, with its lower density and different crystal structure, exhibits lower conductivity compared to silver, copper, and gold. The selection of a conductor for a specific application depends on a balance of factors, including conductivity, cost, weight, corrosion resistance, and mechanical strength. Copper is often the preferred choice for general wiring due to its excellent conductivity and reasonable cost. Aluminum is used in overhead power lines where weight is a significant concern. Gold is used in electronic connectors where corrosion resistance and reliability are paramount. The concept of resistivity is closely related to conductivity. Resistivity is a measure of a material's opposition to the flow of electric current. Materials with low resistivity are good conductors, while materials with high resistivity are poor conductors. The resistivity of a material is affected by temperature, impurities, and the presence of defects in its crystal structure. The temperature coefficient of resistance describes how the resistivity of a material changes with temperature. Most metals have a positive temperature coefficient of resistance, meaning that their resistivity increases with increasing temperature. Some materials, such as carbon, have a negative temperature coefficient of resistance, meaning that their resistivity decreases with increasing temperature. Understanding the temperature coefficient of resistance is important in designing electrical circuits that operate over a wide range of temperatures. The concept of impedance is also important in understanding the behavior of electrical circuits. Impedance is the total opposition to the flow of alternating current in a circuit. Impedance includes resistance, which is the opposition to the flow of current due to the material's properties, and reactance, which is the opposition to the flow of current due to capacitance and inductance. Reactance depends on the frequency of the alternating current. The impedance of a circuit is a complex number that includes both resistance and reactance. The magnitude of the impedance is the square root of the sum of the squares of the resistance and reactance. Phase angle of the impedance is the angle between the voltage and current in the circuit. Understanding impedance is essential for designing and analyzing alternating current circuits. Firstly, silver is the most conductive metal, then copper, then gold, and lastly aluminum. Secondly, holding relays are primarily used for safety.